There are two results which I want to bring up over here. The first one is called the Schwartz identity. Schwartz identity just says that if I take the inner product of two vectors v and w, then the absolute value of this complex number is always going to be less than equal to the product of the norms of these two vectors. I'm not going to prove it, I will just mention it over here. Actually, might not be a bad idea to prove it. For the simple reason that it gives a little bit of practice with using this bracket notation. Okay, let's prove it. So to prove this, okay, it's not a very intuitive proof. Like the starting step is not very intuitive. So just bear with me. So I'll define some vector given by this ket z, which is v minus inner product of omega v over norm of omega square times the ket w. Notice one thing, this inner product over here is a complex number, this thing over here is a real number. So basically this entire ratio is just some number, it's a complex number. So don't get alarmed by seeing all of these things in the numerator and denominator. So it's just one vector minus some complex number times another vector. And what we are going to do is we are going to take the inner product of z with itself. We know that z must always be non-negative. This is, it's basically one of the defining properties of inner product. Length of a vector always has to be a non-negative number. So this inner product of z with itself, now see how to take inner product of this monstrous thing with itself. V minus, I have to take complex conjugate of this, times itself, and now I will do term by term. So v with v will give me this, v with that second term will give me v, wait, first I'll take the number out, wv by w square, and then v with w. Then this second term with this first term. So I will get minus omega v conjugate omega square, and then not omega, sorry, w square with w with v, and then finally last term. So plus omega v star omega v mod, why do I keep calling it omega? Sorry, whenever I say omega I mean w. I don't know why I'm mixing the two up. W square w. Okay, now let's see, some things are going to cancel off. This is just mod v square omega v and v omega are complex conjugates of each other, right? By definition, whenever you flip the inner product you get complex conjugate. So this is just mod square of that. Same thing is happening over here. WV star WV. So this is also WV square plus, again here also WV becomes square. There's a mistake over here, and the denominator in the last term, this should have been to the power 4. This is square. What cancels out? Correct. So you can see I can cancel out two of these terms over here. This and this, they're exactly the same. So I end up with mod v square minus this. And this has to be greater than or equal to 0, because inner product of z and z has to be greater than or equal to 0. So then you can just rearrange the terms and you will see that mod v square mod w square is greater than or equal to mod of wv square. So this is the Schwartz identity if you take square root. So this, if you work through this proof by yourself, it will give you some practice in how to deal with inner products of bras and kets. There's one more identity, and this is called the triangle identity. Triangle identity just says if you sum up two vectors and then you take their norm, this is always going to be less than or equal to the sum of their individual norms. And this is just basically saying that this is just the condition for making a triangle, no? That the length of any side has to be less than or equal to the sum of the lengths of the other two sides. That's all this is. It's called the triangle inequality, not identity, sorry. Schwartz inequality. Why do I call it identity? So Schwartz inequality and triangle inequality. Okay. The very last topic over here with regarding these inner products. I mean, we will keep using inner products all the time, but directly the very last topic that I want to talk about is, let's just introduce it separately over here. So any vector v, I can write in terms of its components. So I can write this as vi, where these i's are the basis vectors. But we also saw that you can write the components you can obtain them as taking the inner product of v with the ith basis vector. So putting this inside this, substituting for vi, what I get is that any vector v is given by but The I part is only in this. So what I'm saying is that V is equal to something times V. But this can just be identity. I mean, if therefore summation over I of ket I bra I is the identity operator, where remember this is a sum over all the basis vectors. So you take all the basis vectors and now you're not doing bra ket, you're doing ket bra. So instead of doing row vector times column vector, you are doing column vector times row vector. So now this is you're doing column vector times row vector. So this is now n cross 1 multiplied by 1 cross n, which is an n cross n matrix. And that n cross n matrix is nothing but the identity matrix. So the next topic that we're going to be talking about is operators, because what is happening over here is that the identity operator or matrix acts on this vector and gives you back that same vector. But this is just a special case of an operator. In general, you can have various different kinds of operators that do different things to a given vector. So the next topic in this discussion is going to be about linear operators. So let's start the discussion about linear operators. So an operator, denoted by this letter capital omega, is it's an object that operates on a vector and transforms it. So for example, if you take a ket vector v, then omega acts on it and gives you some other vector, let's call it v prime. Or if you're talking about a bra vector, here's a bra and the operator acts on it, and over here we put the operator on the right side. So we say that the operator is acting in this direction, this operator, and it gives you a bra v prime. So it's just something that acts on a vector and then transforms it. You think of it as a matrix. If you take if you have a column vector and you operate on it with some matrix, then it will give you some other column vector. Over here, you think of it as there is a row vector and it gets acted on by a matrix to give you another row vector. So here this is 1 cross n with n cross n giving you 1 cross n. In the previous case for the ket, it was n cross n with n cross 1 giving n cross 1. So the matrix multiplication makes sense that way. Now we are not talking only about operators, we are talking specifically about linear operators. So what does this word linear mean? Linear operator means that if I operate this omega on a sum of two kets, so v plus w, then I can just split it up and call it omega v plus omega w. And if I do if there's a scalar multiplication, so omega acting on a times v, where a is a scalar from the field, then I can just pull the scalar out and I get a times omega v. So this is what I mean by linear operator. Okay. Geometrically, what is it? What exactly is this operator doing? So once again, we'll take our simple example of R2 because it's easy to visualize. Geometric interpretation So in R2 I have my two-dimensional plane. Let's say I start with some vector v. What can an operator do to it? If I take an example of the identity operator, identity operator acts on v and gives us back the same vector v. So it does nothing. So okay, that is one trivial example of an operation. So identity is a linear operator. I can have one more operation which just multiplies this v by a scalar k. So this does nothing. This one just stretches the vector by that factor k. Stretching or shrinking depending on whether k is greater than 1 or less than 1. In general, it is just changing the length of the vector. Okay. Are you familiar with... Okay. Let's take an example of an operator which looks like this: 1 over root 2, 1 over root 2, minus 1 over root 2, 1 over root 2. So if I take any vector v and let's denote it by x comma y. So this point over here is x comma y. What happens? This becomes 1 over root 2x plus y, 1 over root 2 minus x plus y. So it has somehow changed, it has taken my original vector v and turned it into some other vector v prime. If you try to plot this point, this vector 1 over root 2 x plus y and 1 over root 2 minus x plus y, what you will find is that it is just this original vector v but rotated by an angle 45 degrees. So an operation can also take a vector and rotate it. In general, any rotation about an angle theta can be written in this form: cosine theta, sine theta, minus sine theta, cosine theta. So what this operator omega will do is, every vector in the plane, it will rotate it by an angle of 45 degrees clockwise. Okay, so this is one possible operation, just a rotation. Of course, this is in 2D. In 3D also you can generalize it. In 2D there's only one plane, the xy plane, in which you can rotate. In 3D you can rotate in the xy plane, in the xz plane, and in the yz plane. So you can have 3 different rotations over there. Okay. Let's take one more example. What do you think about this operation? 0, 1, 1, 0. What does this do? So if I operate this on some point x, y, I will get yx. So it flips the x coordinate and the y coordinate. So what this operation actually does is, it is a reflection. It is not a rotation. Should make a different diagram. It is a reflection about this 45 degree line. So any point which is over here and has coordinates x comma y, it will reflect it about it and bring it over here where its coordinates are y comma x. So this is a reflection. In general, a reflection about an axis or about a line with whose inclination is theta is given by this. So this is one more thing that an operator can do. It can flip points about any given axis. Points are in vectors about any given axis. So it takes this vector and transforms it into this vector. So in general, an operator can either do nothing to a vector, or it can change its length, it can shrink it or stretch it, it can rotate it, it can reflect it, or in general it can do any combination of these. So geometrically, this is what operators do. They take any vector in your space and they turn it into some other vector in your space. Okay, I think we will stop here for this video, and then in the next one we'll start writing down detailed calculations about operators. Okay, so we stop here.